This is the fourth session in graphical representation of motion in a straight line. We will be looking at acceleration as the gradient of a velocity time graph, in a similar way that previously we looked at velocity as the gradient of a displacement time graph. For acceleration, the change in the velocity value divided by the change in the time value gives you the acceleration. So we're looking at rise over run once again. In the graph that's there, the rise is 15 take away 5, and the run is 6 take away 1, and we get 10 divided by 5, or 2. So the acceleration is 2 meters per second per second. Consider this example. Here the object has an initial velocity of 15 meters per second, and its velocity decreases by a constant amount of -2 meters per second every second. We can say that the object experiences a constant acceleration of -2 meters per second per second. The change in velocity then is towards the left. In this example, have a look at what the graph tells us. The object has an initial velocity of 0 meters per second, and its velocity is increasing by a different amount each second. The increase between the first and second second is 5 meters per second, but if we look between the fourth and fifth second, the increase is 11 meters per second. So in this case, the acceleration is not constant, the acceleration is increasing. The velocity is increasing and at an increasing rate. Here's another example. Let's read what the graph tells us here. The object has an initial velocity of 0 meters per second. It speeds up, but its velocity is increasing by a smaller amount every second. The increase between the first and second second is 7 meters per second, but if we look between the fourth and fifth second, the increase is only 1 meter per second. So in this case, acceleration is not constant, the acceleration is decreasing. The velocity is increasing, but at a decreasing rate. One of the things we want to know is the acceleration at a particular point in time, or the instantaneous acceleration. Here, let's have a look at 3 seconds. And at that point, the gradient of the tangent to the velocity time graph is given by the rise over the run. And reading the figures off the graph, that's for the rise, it's 27 minus 7, and for the run, it's 4.3 minus 0. Simplifying that, we get that the instantaneous acceleration is 4.65 meters per second squared. We can also find the displacement from a velocity time graph. So far we've seen that the acceleration of a body is determined by calculating the gradient of the velocity time graph, but the displacement of a body is equal to the area between the velocity time graph and the horizontal time axis. Let's take a simple example. Consider a body that's moving at a constant velocity of 5 meters per second for 4 seconds. The displacement during that time is given by x equal the velocity of x times the time, so that's 5 times 4, and the displacement will be 20 meters. Graphically, that's the same as calculating the area between the graph and the horizontal axis. So now we can look at more complex arrangements. The relationship of displacement to area in a velocity time graph holds even if the graph is curved, as in the illustration. The area between the velocity time graph and the horizontal time axis between 4 and 8 seconds is equal to the displacement of the object between 4 and 8 seconds. As you might expect, the following rules apply. If we want to determine the displacement using areas in a velocity time graph, well, velocities above the horizontal axis are positive, and they indicate that the body is moving to the right. And if we consider areas above the horizontal axis are positive, and since the body is moving to the right, they represent a displacement to the right. Similarly, velocities below the horizontal axis are negative, and they indicate that the body is moving to the left. So areas below the horizontal axis are negative, and since the body is moving to the left, they represent a displacement to the left. Let's see how that works. In this example, the object moves right, slows down, stops at time equals 4 seconds, and then between 4 and 8 seconds it travels to the left, speeding up. So on the graph you can see area A1 is positive, meaning displacement is to the right, but area A2 is negative, meaning displacement to the left. Performing the calculations, area A is a triangle, and the area of the triangle is a half times 20 times 4, or 40, while area A2 is a triangle with area minus a half times 20 times 4, so minus 40. And that tells us that the displacement at time equals 8 is equal to the area of the two triangles, which is 40 and minus 40, so the displacement is 0. In other words, the object is back where it started. It's travelled 40 metres to the right and 40 metres back to the left. So the total distance that the object travelled is 80 metres. The extension of this kind of work takes us into calculus. Finding the gradients and calculating areas associated with graphical representations of functions is essentially the concern of calculus. The process is called differentiation, and that's what's involved in determining the gradient of a tangent. The process in calculus called integration is what is involved in determining the area between the graph and the x-axis. And that's the end of these 4 sessions on graphical representation of motion.